Hey everyone, welcome back to The Explainer. So today we're tackling something that is honestly a massive headache in system design, and that's querying highly connected data. If you've ever tried to write a standard SQL query that has to traverse, say, 5 levels deep into a social network, or maybe map out some convoluted routing path, you know exactly what kind of pain I'm talking about. When you're dealing with really complex relationships, think organizational hierarchies or massive knowledge graphs, standard relational models just kind of hit a wall. Now, sure, there are specialized graph query languages out there like Cypher or SparkQL. But today, we're actually going to look at two radically different alternatives that sit on completely opposite ends of the spectrum. We're talking about Datalog and GraphQL. One of them gives you this almost limitless recursive backend power, while the other gives you strict, intentional limitations designed to protect your modern client-side apps. It really is a tale of two extremes, and getting a handle on both will absolutely change how you think about your application architecture.
Okay, let's just dive right into it. First up, we're going to look at querying connected data in general. Then we'll break down Datalog fundamentals, pivot over to GraphQL's limitations, and finally wrap up by comparing the two alternatives.
Starting with Section 1, Querying Connected Data, and why we're even searching for alternatives in the first place.
So here is the million-dollar question we're trying to solve. How do we efficiently query highly connected data when standard relational models fall short? Look, if your app is mostly one-to-many relationships, like a blog post with a bunch of comments, traditional standard joins are totally fine. But what happens when many-to-many relationships take over? What if your query needs to traverse a completely unpredictable number of edges? Like, imagine an org chart, right? You need to find every single employee who ultimately reports to the CEO. Some are 1 level down, some are 2, and some might be 15 levels down. In traditional SQL, you literally have to write out your joins in advance for every single hop. But in a rich graph structure, you usually have no idea how many hops it's going to take. Doing that in SQL means writing these awful recursive common table expressions that are just a nightmare to read and optimize. It completely bogs down your database. We desperately need a better way to handle these unbounded variable depth connections.
Which brings us to Section 2, Datalog fundamentals and the absolute power of recursion.
To really get Datalog, you have to completely flip your mental model. It's technically based on the relational data model, but you can go ahead and forget about massive, wide tables packed with null values. In Datalog, your foundational building block is just called a fact. A fact corresponds to a single row in a table, but it reads way more like a logical statement. So imagine you're building a location database. A fact would be this simple atomic statement, like Lucy was born in Idaho. That's it. These basic statements form the absolute ground truth of your database. You're basically building your universe atom by atom, just stating what is undeniably true, without stressing over how it's all going to connect later in some massive join table. It's a purely declarative approach.
And it's actually kind of wild, because Datalog literally came out of 1980s academic research papers, but today, it's the secret weapon powering some incredibly complex modern architectures. It might not be super mainstream for your average front-end dev, but it is the engine of choice for these highly specialized niche databases. We're talking about heavy hitters like Datamic, LogicBlocks, CozoDB, and even LinkedIn's internal LI Graph database. These massive systems use Datalog because it is just overwhelmingly expressive. When you have to resolve deeply nested permissions or analyze real-time professional networks across millions of users, Datalog handles those recursive graph traversals better than practically anything else.
This visual perfectly illustrates what we're talking about. It's a web of facts. You've got Lucy, born in Idaho, which is in the US, which is in North America. Then you've got Elaine, born in St. Lo, France, which is in Europe. They're married and they both live in London. Now, imagine writing a normal SQL query to find out if anyone born in North America is currently married to someone born in Europe, and where they live right now. You'd have to traverse up the map from Idaho, up from St. Lo, check the marriage edge, and then traverse down to London. Doing that without knowing exactly how many subregions exist between a city and a continent, you'd be writing incredibly deeply nested self-joins that would literally bring your database to a crawl. But Datalog handles this whole web elegantly just by using derivation.
So, how does it actually execute that without breaking a sweat? It's a step-by-step logic process. Step 1. You define your base facts, those ground truths, like Lucy and Idaho. Step 2. You define logical rules that reference those facts. Step 3. Datalog uses those rules to derive new virtual tables on the fly. But step 4 is where the magic happens. Datalog rules can invoke themselves. That's recursion. You tell the system just once, hey, location A is inside location C,
if location A is inside location B and location B is inside location C. That's the whole rule. Datalog takes that single self-invoking rule and just spins it. It effortlessly climbs from city to state to country, dynamically calculating the entire graph without you ever specifying the exact number of joins. It just keeps spinning until it finds the answer. It is phenomenally powerful back-end logic.
But wait a second. What if you absolutely do not want that kind of raw, limitless back-end power exposed? If you put a recursive engine that spins like a top on the public internet, that power becomes a massive liability. And that brings us to a hard pivot, GraphQL and the intentional shift toward client-side simplicity.
Let's look at Section 3, GraphQL limitations and why restriction is actually a superpower.
There's this quote directly from the source text that really hits the nail on the head. GraphQL is a query language that, by design, is much more restrictive than the others we have seen. Now, usually in software engineering, restrictive is a bad word, right? Developers always want more power, more flexibility, but GraphQL is optimizing for something completely different. It is highly pragmatic, built specifically for client software running on a user's device, like your iOS or Android app or a React frontend. Those environments, they don't need to mathematically calculate transitive closures. They just need specific data right this second to paint a screen.
So to serve those mobile clients safely, GraphQL intentionally bans the exact things that make Datalog so cool. There are strictly no recursive queries allowed, none. And no arbitrary search conditions either. You can't just ask a GraphQL endpoint to find everyone in the US who moved to Europe unless the back-end engineers literally hard-coded that specific search into the API. Why be so strict? Because GraphQL queries come from the public internet, untrusted sources. If a client could submit a recursive query, a malicious actor, or honestly even just a buggy mobile app could accidentally trigger a catastrophic denial of service attack. They could ask for an infinitely deep traversal and completely melt your database servers. GraphQL willingly trades away that back-end expressiveness to guarantee front-end safety.
Instead of open-ended searches, think of a GraphQL query like a super precise restaurant order. In a traditional REST API for a chat app, you might have to hit 3 different endpoints just to get a user, then their channels, then their messages. That's underfetching, and it's terrible for mobile networks. Or you hit one endpoint and get a massive payload of 50 fields when you only needed 3. That's overfetching, and it drains user batteries. GraphQL fixes both. The client query explicitly asks for exactly what it wants: the channels, 50 messages, sender names, and profile pics. And the server sends back a JSON document that perfectly mirrors that exact requested structure. No more, no less. If the UI team drops the profile pic from the design tomorrow, they just delete that line from the query and the back-end server doesn't have to change a single line of code. It's a real game changer for front-end agility.
Moving into Section 4, let's compare these alternatives and look at this spectrum of control. So, the absolutely crucial takeaway here is understanding the trade-offs between these two. Just look at the breakdown. Datalog is entirely focused on back-end complexity. It gives your internal systems this highly expressive, recursive power, and it returns data as derived virtual tables. GraphQL is the exact opposite. It's all about front-end UI simplicity. It is intentionally restrictive to protect your servers, and it returns a perfectly mirrored JSON document tailored exactly for what the screen needs. If you try to use GraphQL for deep data mining, you're going to hit a wall. And if you try to hook up a raw Datalog engine directly to a mobile app, you are basically asking for your service to crash. And that leaves us with the ultimate question for your own systems. Both of these deal with graphs. Both connect highly interrelated data, but they exist in totally different worlds. Are you building robust internal tools that need deep, recursive traversals to uncover hidden patterns? Or are you building a snappy, public-facing mobile app that needs strict, predictable data delivery? Which worldview does your next project actually need? Think about it. Thanks for hanging out with me for this explainer, and I'll catch you next time.